Deep in the Egyptian Sahara, summer temperatures can reach 118.8 degrees Fahrenheit. Combined with less than 9 inches of annual rainfall, the environment is one of the most thermally aggressive on the planet. For hundreds of miles in every direction, the landscape is an ocean of lifeless sand. Yet completely isolated within this wasteland are lush palm groves, like those found in the Siwa and Dakhla oases. These permanent agricultural settlements are massive in scale, having sustained tens of thousands of people for thousands of years. From above, there are no visible rivers or streams feeding this extensive ecosystem. The survival of these communities depends on a massive hydrological engine operating entirely underground. This water begins as sparse rainfall spread across thousands of square miles. Over time, the moisture filters down through the sediment and collects in a subterranean layer called an aquifer. Gravity pulls this underground water table toward the lowest elevation points in the desert. Many oases sit inside deep geographical depressions. The Siwa Oasis, for example, is located 19 meters below sea level, effectively acting as a structural funnel for the surrounding groundwater. When this pooling water hits an impermeable layer of rock or clay, the resulting pressure forces the water upward. It seeps through the ground to create surface springs without the use of mechanical pumps. This geological process provides a steady water source, but raw water alone is vulnerable. At 120 degrees, surface water risks evaporating before it can support a large-scale ecosystem. So why doesn't the water reaching the surface immediately vaporize? Evaporation does occur, but it triggers a physical defense mechanism known as the Oasis effect. Converting liquid water into gas requires energy. The water molecules strip this energy from the surrounding air in the form of heat, creating an endothermic reaction. The act of evaporation produces a localized refrigeration field, actively cooling the immediate area. Ancient populations expanded this cooling effect by planting massive strategic forests, such as the 50,000 date palms found in Dakhla. These trees increase the area's albedo. Unlike the dark desert floor, which absorbs heat, the dense green canopy reflects solar radiation back into the atmosphere. The canopy also acts as a physical shield, trapping the moisture released through plant transpiration. This keeps the cooled, humid air near the ground, instead of letting it dissipate. By combining a geological water funnel with an engineered canopy, humans created a self-sustaining thermal shield. This engineering allowed for the development of permanent communities, like the medieval village of Al-Qasr, built inside the Dakhla oasis. The village utilizes a dense adobe layout to maximize shade, harmonizing the architecture with the oasis's cooled air. These ancient settlements established a functional model for climate engineering long before the industrial era. Modern cities currently face a similar thermal challenge. Dense concrete and asphalt absorb and radiate heat, creating the urban heat island effect. To address this, urban planners are now studying the mechanics of the Oasis effect. Integrating water sources and high albedo vegetation into city grades, as seen in New York Central Park, replicates the desert canopy to lower local temperatures. The same principles that allowed life to persist in the Sahara now provide the framework for cooling our modern urban environments.